Today we're talking about vectors. So what is the vectors? Vectors actually is arrays. You may ask, you already talk about arrays and immutable arrays in the previous video. Why are you talking about arrays again? Okay, actually this is somehow of special kind of arrays. At first, we need to say that this is only integer indexed array. As I said in previous video, you can make in Haskell an array of any type which represent the index constraint type class. And you can use this type as an index of the array. But here you can use only integers. And I think this gives some optimizations. And also with the vectors, implement the string fusion optimization, which allow you to, for example, when you have some array, big array, and you do, for example, two maps, this leads to two loops over this array, but Haskell can identify them and merge these two maps into one loop. Okay, and also Haskell can optimize situations then you don't need to create a vector. For example, then you summarize a big range. Actually, you don't need to create at first this vector in memory, and Haskell can save your memory in this situation. Also, you can do slicing these vectors, and actually vector de facto standard package in the Haskell ecosystem. And also vectors provide much more rich interface than arrays and immutable arrays, and this interface mimics to list-like interface. Every time you want to use a vector, you need to determine which type of the elements you want to use in this vector. And in this way, vector has different types of implementation. There is 4 types of implementations. I think the first is box vectors. They can hold any Haskell type. And the next type of vectors is unbox vectors. They have adaptive representation for some special types. For example, if you want to store on some primitive integers or floats and so on. And also there exists a storable type of vectors. This type of vectors has some specific internal implementation. The main point that you can use this type of vectors with some foraging language like C. And the last is primitive type of vector. This is the same as this unboxed, and I think it is not. I think it is not recommended to use because it is better to use unboxed. Because it is more flexible with no performance cost. Okay, we have many types of the vectors, but of course we want to work with them in somehow in one interface with all of them. We don't want to have many implementations. Specific implementations which we want to work the specific interfaces with them. We want to somehow generalize them, and for this there exist special type classes which represented in a Data.Vector.generic. And actually there are two of these type classes: the type class for mutable vector and for the immutable vectors. Okay, let's start from this mutable vector type class. We need to provide some vector for it, And as you can see here, this vector need to have a kind of start to start to start, and this is state. This state parameter represents state because we have this mutation here, and they need to express this in this data type, so we need to provide some state in it. Also, we have this A type, which represents the element of the vector. Okay, and this type class defines some function which needed for mutation of the vector. We can take the length of the vector, we can take the slices of the vector, we can check if vectors overlaps or not, we can create the vectors. Of course, this will be inside the stmonad. We can initialize the vectors, replicate vectors, read the elements from the vector by its index, and write elements to the vector by its index. We can also clear vector, set vector to some value, copy the vector, move the vector, and grow the vector. So if we have a vector of some fixed length and we want to expand the number of elements which we want to store, we can use these functions. Okay, this was the first type class of the generic interface, the type class which allow us to do the mutations. And now let's look at the second type class, which allow us to do the work with the immutable types, with all these immutable types of the vectors. And here you can see these implementations of all the types of the mutable vector data. Now let's look at this type class. Okay, generic interface to immutable vectors. You can see here that to implement this type class called vector, they need to provide the vector and the type of the vector and the type of the element of this vector. And as you can see here from type signatures, this vector has the kind from star to star, because when we want to construct a vector, we need to provide the element. I talk about immutable vector. We only need to provide the type of the element of the vector. So that's why this start from star to star. And also one point here is that every immutable vector, so we have some kind of vectors, as I said earlier, need to be associated with this mutable version. And this association need to be encoded with, actually it is encoded with the mutable type family. What is a type family? Okay, you can think about this type family as a function from types to types. And this is injective function. This function takes some type of immutable vector and produce to us the corresponding mutable version, type version of this vector. Okay, let's look at the mutable type family definition here. They have actually we have this signature for this type function, and what it takes, what it said. It said that if you give to me this type of the vector, of the mutable vector from star to star, I will return to you this mutable version of this type of the type of the mutable version of this vector, and it has the kind of star to star to star. We have here additional star because we need to represent a state, because the mutate, this is a mutable type which represents a mutable type. It's mutate and it needs to be represent state. That's why we have additional type here. And this say that they have, I think, something like functional dependency here, that if we have mutable version, it determines the immutable version. Okay, and as I said, this is injective function. So you have the S domain, you have these immutable types, and as codomain, you have the corresponding mutable types. And you have the injection here, you can go to both sides. And here you can see the definitions of this function, of this type family function. You can go click to the source code and look what happens here. Actually, the say for every type of this immutable vector, this set corresponding mutable vector, and so on for every type of these modules. Sorry, every type of these vectors. So we have 4 vectors. We have 4 type of vectors, and we have these 4 type of corresponding instances which do this mapping. And now let's look again at our vector type class. You can see here that to instantiate this vector type class, you need to provide this vector, this type of vector. And if you take the mutable version of this vector, it needs to be constrained to the mutable vector type class. Okay, and of course we need to provide this type or this type class also. And if you provide this, you can implement the interface for immutable vectors, and you can see all this rich implementation. Okay, it's very long. Actually, no. Actually, it is not very long. It has some functions. For example, you can freeze the array. You take mutable arrays and move it into immutable arrays. Array. You can unfreeze this array to move immutable to mutable. You can get the length. You can slice. You can yield the element in a given position inside the monad. You can copy, and also there is some method for optimizations. I don't want to talk about them. And you can see here all the instances which implement this type class. So actually this is instances for every of these 4 types. And here we have we have actually all these functions which represent a list-like interface, with which you can work with this vector. So we have some accessors. You can take length of the vector, check the vector is null or not. You can do indexing. You can take head, you can take last. And so on. Also, you can do monadic indexing if you want to go into context. After that, you can take head in the monad context last. Also, we can do the slicing, splitting. Okay, so actually this is a list, I think. It's mimics to list. And if you know lists, you can use all these. So this is a creation functions, monadic creation functions, folding, unfolding, I think that's all. Enumeration. You can do concatenations, modifications, and so on. So as you can see, this interface is very rich. Okay, I will put this link in the description. You can see what, if you're interested in these functions. Okay, now let's do some examples. And let's demonstrate how can the work with immutable vectors at first. Okay, we need to import this module. Let's import it as qualified. And as v. Okay. And let's at first let's just create our vector. So to create a vector, we have from list function, for example. This is not just one way of doing this. I think you can look at documentation how to where exist some other functions, but I will use from list function, and I will create the list which contains some strings. Okay, and let's give name to it, for example, our vector. Okay, we create this. After we create this vector, we, for example, can extract a value from this vector, from this immutable vector. Okay, let's do it like this. We have this function to the successor to the vector, and we, for example, get the element with the index 1. This will be b element, and let's just print it to demonstrate that it is as it is. It works. Let's demonstrate how it works. Let's load our module b. So I think I need to change directory here. Okay, I load the file and it's compiled. Now let's run our main function. And you can see here that they have printed this element at index 1, and it works as expected. Okay, next thing what we can do, we can, for example, create a new vector. From this we have the function for updating. We can take our previous vector and use this type of function to update, and we also need to provide the information about which elements we want to update, and this encoded their list of pairs. For example, we can what if I want to update one element, the x, and I will write this like this. So after this I can extract my element again from this new vector using my accessor, and I can print this element. Let's try to reload. Oh, I have error. Of course, I need to fix this, and let's reload and print. Okay, now you can see that our at first it was b and now it is x, so vector is modified as expected. And for example, what we can do, of course there's many functions. I will just try a few of them to show the main principle how we can work. So let's, for example, create the slice. So I will put this slice into another vector. We have function tslice for this, and they need to provide start position of the slice. For example, I want to slice from one, and the length of the slice. For example, I want to slice of just one element, and let's provide our v1 view updated x. And after this, we can print this v2. Okay. As you can see, I get the slice of the length 1. This is only x, but of course I can take the slice of the length 2, and this will give me the 2-element vector. Okay, this was how can we work with the immutable vector. But what if we have mutable vector? Okay, let's call this section like immutable vector example. And now I want to make another action, which is I will call this section as immutable vector example, and of course it will be inside IO monad because we do side effects with mutable vectors. Okay, at first, how can they create the mutable vector? We can create it with again, we can create like exactly like here. So I just copy this string here, and after this I need to throw so somehow unfreeze this vector, and this will give me the vector, the mutable vector. Okay, let's look at this function. And as you can see, they need to provide a vector immutable, and as a result we will have the mutable vector inside primitive monad. Primitive monad is just it's IO monad or ST monad, one of them. Here we inside IO monad, so it will resolve as IO monad. Okay, let's provide our vector d, and this is a monad. Let's extract a vector from this monad, and this will be mutable vector. Okay, now we have this mutable vector. We can, for example, write to this vector. So we can let's at first we need to import model Data.Vector mutable. Let's import as nv, and now we can use this function nv write. I think nv write. Where is this function? I don't know why it doesn't see types, it doesn't show me type signature. Okay, but what we need to provide? We need to provide our mutable vector as the first element to this function, index, and element which we want to modify. And this thing will create an action which modify a vector with the empty tuple as a result. So this is a monad which will up the empty tuple value. And the side effect is a modifying of this vector. After we do, okay, if we have errors, I will try to compile and we will see them. And after this, what I want to do? I want to unfreeze this vector. Okay. Actually, not unfreeze, to freeze. And we have this freeze function. We need to provide the mutable vector again. This is our MV. We freeze it and we put it to v1. This is our new immutable vector. And now we can print it. Print this v1. Okay. Well, now it showed me the type signature and the write. As you can see here, they provide an m vector, int and a, and have this monad, primitive monad, IO in our case, and the empty tuple. So let's reload, let's run. Let's run unvect. And here you can see that we have modified vector. This is our x, modified x. So they do modifications. Now let's compose our two actions and make it as main. Let's run, let's main, and we have these two examples one by one. Execute them. Okay guys, this is short review and quick start. I think it will help you to quick start with vectors. And thanks for watching. Push like button, push subscribe button, and see you in the next video. Bye bye.